next speaker today is Dr. Peng Jiang. Dr. Jiang received his PhD in computer science from Princeton University in 2013, and his BE from Tsinghua University back in 2007 with the highest honor. He started postdoctoral research at Dana-Farber Cancer Institute and Harvard Medical School of Public Health from 2013, and it focuses on algorithm development and large-scale data integration for knowledge discovery in cancer biology. Today, he'll present his work in cancer immunology from a unique perspective, taking advantage of the publicly available big data. So now let's welcome Jiang Peng.
What a fantastic introduction from Shen. What a fantastic scientific report. So it's really my great honor today to share some of our recent progress with everyone here and welcome for your valuable feedback. So as probably everyone here knows that immunotherapy is really one of the biggest breakthroughs in the field in this year. Comparing to the conventional targeted therapy, immunotherapy will achieve very long-lasting clinical benefit on a subset of the patient. However, a challenge and issue right now is why only a subset of the patient could get the benefit, and the majority of the patients do not even get the initial response. So, in order to find a kind of a prognostic biomarker to predict the therapy response, if you look at the previous successful example of genomic biomarkers, for example, from MammaPrint, from IconType DX, you need a large scale of training data, like hundreds of patients paired with their genomic profiles and the clinical outcome. However, for immunotherapy, nowadays such kind of data is very limited. So far as I know, the very comprehensive genomic data only exists for melanoma, like for both anti-PD-1 and anti-CDI4 in the medium scale. And the genomic data are also partially available for lung and kidney cancer. But for most of the other cancer types, even you only see the clinical trial, but the patient genomic data are not available, even in the industry nowadays, by lots of limitation factors. However, alternatively, there are a large set of another type of data, which are the cancer clinical studies without immunotherapy, but they do provide you the genomic profiles of the tumors and their clinical outcome. So for example, the database of TCGA, BRITOC, Metabolite, and NCBI GEO has lots of such kind of resources. So even though this type of clinical study of cancer may not be conducted under immunotherapy, but they may contain very rich knowledge of tumor immune escape mechanisms. So our hypothesis here for this study is if we can somehow repurpose all of those previous studies and build up a reliable biomarker to predict the signature or the potential of a tumor for immune escape, this biomarker may serve as a very reliable way, or may serve as a very reliable surrogate biomarker to predict resistance to immune therapy. Okay. Thank you for the So previous studies has identified two broad categories of tumor immune escape. So in the first category, the tumors are infiltrated with lots of cytotoxic T cells. However, those T cells are in dysfunction state and cannot eliminate the tumors. In the second broad category, the tumor are really immune cold. The T cell even doesn't get a chance to infiltrate into the tumor and eliminate that. So our computational framework will follow this scheme to identify biomarkers to predict the overall level of T cell dysfunction in immune hot tumors and overall level of T cell excretion in immune cold tumors. So for the first category, by definition, T cell function means the T cell successfully infiltrating the tumor, but they cannot control very efficiently. So if you look at the TCGA data and look at our patient survival, you can classify the tumors into two different categories according to the gene expressions of a set of well-known like marker genes of cytotoxic T cells. So we can see that for the tumors infiltrated with kind of a reasonable amount of cytotoxic T cells, their survival tends to be significantly better than the other portion of the patient. However, such kind of clinical benefit is not always true for patients. So for example, if you subdivide the melanoma patient according to the expression status of the third gene, I use banana here as an example. You can see that for the patient with a top 1/3 expression level of banana, indeed, high infiltration of cytotoxic T cell means a better survival. However, for the patient with the low expression level of banana, you see that the high infiltration level of cytotoxic T cell doesn't mean any clinical benefit. And gene melanoma, you can see the full gene name, melanoma antigen recognized by T cell. So it's a gene highly expressed in the tumors, and the T cell can recognize and eliminate this tumor. So this retrospective study is coherent with the previous knowledge. And if you categorize the patient tumors according to the gene expression of another gene, which is the famous PD-L1, developed from the seminal work of Gordon here, like you can see that for the tumors with high expression of PD-1, you see exactly the reverse trend. So this example is from triple-negative breast cancer. With high PD-L1 expression, the high infiltration of cytotoxic T cell doesn't mean any clinical benefits. But the patient tumors with low PD-L1 level, we do see the better clinical benefits of cytotoxic T cell infiltration. So from these two retrospective examples, you can see that this type of previous knowledge can be well recaptured just from the data. So the question is, can we find something new here? So in statistics, when you look at the relationship between two factors, which is the CYT, the cytotoxic T cell infiltration, and the clinical outcome, depending on third gene, we normally use a test called the interaction test to find our relationship with each other. So by this is just based on very simple multivariate model by putting an interaction term between cytotoxic T cell level and the gene expression level of another gene. So if the interaction coefficient here is positive, this means the higher level of another gene, like PD-L1, will increase the death hazard. If the coefficient is negative, this means the expression level of the partner gene will reduce the death risk. So this is the way we use a statistical approach to systematically evaluate each gene in the human genome for their potential effect on T cell function. So here's an example. It's just a very simple Cox-Ph regression with all of these confounding factors and the interaction terms here. And as we expected, the PD-L1 had a significant positive interaction, means increase of hazard, and the melanoma had a significant negative effect, means decrease of hazard. So we can apply this kind of interaction type systematically across 235 large-scale clinical studies we collected from lots of database. Each study is a clinical data set on one specific cancer type. And I just pick a bunch of top score genes here as an example to show everyone. So for example, you can see that among these top genes, the PD-L1 consistently have the positive interaction coefficient across different cancer types. And another famous example, TGF-beta1, which is a kind of a very well-known immune suppressive factor, you also see the consistent positive value here. And SOX10, some other genes will have the opposite set scores. For example, SOX10 in some recent CRISPR screen study, they demonstrate that knocking out SOX10 will increase, will make the immune cell more resistant to T cell mediated killing. Fortunately, our interaction test captured all of this knowledge. So the key question is, normally for computational people, when we develop some statistical approach, we can always apply this to a large set of data, but whether this makes sense in general. So we need some gold standard to test whether our scoring scheme here makes sense. So we use some previous published gene signatures related to this T cell dysfunction, see whether our scores are consistent with previous studies. So for example, the Kai-Wuking Pinifig lab did in vivo SHR screen in the mouse T cells and test which gene knockdown will increase the T cell infiltration and expansion efficacy. And there are also some mouse models of exhausted T cells. If you compare their gene expression features, or compare their gene expression profiles to activated T cells, you might find some genes specific for T cell exhaustion. And also, the Andy Min lab has a mouse model. Their tumor are intrinsically are acquired drug resistance to anti-CTLA for treatment. And you can compare this kind of drug-resistant tumors versus the parental B16 tumors. So in each study, they have a bunch of top genes and bottom genes related with T cell dysfunction. You can see, on average, these studies are very coherent with our dysfunction scores. So recently, the Schettinger lab from Memorial Sloan Kettering has published a set of very interesting works. So they have a mouse model of T cell exhaustion, and they demonstrate that in their T cell exhaustion model, when the T cell gets into the process of exhaustion in early days, these exhausted T cells could still be rejuvenated by the anti-PD-1 treatment. However, after 14 days, the exhausted T cell from their model can no longer be rescued even after anti-PD-1 treatment. So we do a Pearson correlation, test their gene expression profiles of their T cells in different stages of exhaustion and our dysfunction scores. You can see from these 5 different cancer types that our method works best, it seems our signature is more correlated with their T cell exhaustion in later stage. So which means that our dysfunction score is sort of capturing the state of T cell exhaustion that cannot be rescued by anti-PD-1 treatment. So this is a brief summary of our first part. So we have a statistical method can repurpose the human clinical studies without any immunotherapy and apply this kind of interaction test to find some signatures related with T cell dysfunction in immune hot tumors. However, tumor not only escape the immune surveillance by T cell dysfunction, and there's another big category that the tumor could use a T cell exclusion mechanism to evade the immune surveillance. For this is really a huge literature history. Like there are incredible amount of studies trying to identify the potential factors driving T cell exclusion. So we just reviewed the previous literature and try to evaluate the people's previous paper and see whether we can really replicate their conclusions using the data-driven approach. And eventually, after reviewing lots of papers and try lots of different ideas, we found that there are 3 cell types, and their gene expression profiles are really a strong indicator of T cell exclusion. So here is the explanation. So this example is still from the TCGA melanoma example. So each dot here is one melanoma tumor sample. And on the x-axis, we plot the Pearson correlation between the MDSC, like myeloid-derived suppressor cell gene expression, and the patient tumor gene expression. On the y-axis, we just show you the gene expression estimators of cytotoxic T cell infiltration. As you can see that from MDSC, tumor-associated macrophage M2 status and cancer-associated fibroblasts, a higher correlation between the gene signature of tumor and the cell type normally indicate a strong depletion of the toxic T cell. So which means this previous knowledge can be well captured using a genomic biomarker approach just based on gene expression. So we use the average expression of these 3 cell types. As you can see, we get a strong anti-correlation. We also check that whether this kind of strong anti-correlation is also observed in other cancer types. So in this plot, 1 dot is 1 cancer clinical studies from some publication. There are more than 200 cancer clinical studies we collected. You can see that our gene biomarker here is consistently negatively correlated with infiltration level of cytotoxic T cells. So which means that our biomarker of T cell exclusion kind of is a very general applicable biomarkers to most cancer types that we collected. So here is just our view of like we use some computational method to develop some biomarkers to test the overall level of T cell dysfunction and T cell exclusion. Then it's time to check whether this biomarker could really predict the immunotherapy outcome. So we call our biomarker TAG, which means tumor immune dysfunction and exclusion. So to the best of our knowledge, there are only two kind of publicly available data sets of checkpoint blockade therapy paired with clinical outcome and pre-treatment tumor gene expression profiles. The panel A is the anti-PD-1 study from the Tony Rivas lab at UCLA. The panel B is from Ali Van Allen and the Garaway lab, published from Dana-Farber. So each column here is one patient. So we first look at infiltration level of cytotoxic T cells in each cohort and categorize them into either immune hot tumor or immune cold tumor. And then for each patient, for immune hot tumors, we just sort all of these patients according to their expression correlation with our dysfunction signature. And for the immune cold tumors, we just sort this patient according to their correlation with our exclusion signature. And each number here is a patient index in the original publication. So you can see that this blue and red colors is the clinical outcome from each study. You can see that it seems in general our sorting is consistent with the clinical outcome in each study. And then we just systematically test whether the correlation with our signature here could really serve as a predictor for the responder status. So we have a scaled correlation for each patient. And then you can see that in both studies, it seems that the non-responders have a higher scaled correlation than the non-responders. So computationally, when we test how does a predictor could predict some outcome, we normally use a kind of curve called the draw curve. In the draw curve, you use different threshold to cut your predictor and do the prediction and compare our predicted responder status with the real clinical outcome. So each methodology you could get a draw curve, like a performance curve for each method on the different level of false positive rate and false negative rate. If your predictor is making a pure random guess, the performance curve will stay on the diagonal. This means it's really bad. If your predictor is making a really good prediction, 100% accurate, the performance curve will stay on the upper left corner. So a better method will normally stay above the performance curve of the worst method. So you can see that people use mutation loss a lot to predict the immunotherapy response. And the FDA approved the PD-L1 gene expression by IHC test as probably the only clinical approved biomarker of immunotherapy response. And the TAG, the right curve is our biomarker. You can see that in both anti-PD-1 study and anti-CTLA-4 study, the prediction curve of TAG is consistently or mostly staying above the other two commonly used biomarkers. And you can use the area under the performance curve as one single measure to quantitatively measure to test how good predictor is. So we call the area under curve, the higher the better. So the immune response, the checkpoint blockade response biomarker is really very intensively researched topic right now. So there are several kind of biomarker already published in the literature. So for example, mutation loss. And interferon gamma is a commercialized biomarker by the NanoString technology company. They use their NanoString technology to measure 6 gene expression related with interferon gamma response as a biomarker of checkpoint blockade response. And some people also developed some similar computational genomic approach called the immune phenotype score to predict the immunotherapy response. And also Steve Ehrlich's lab from here, like from the Harvard Medical School, and see that the overall copy number variation of a tumor is a good predictor. So we evaluate all of these biomarkers that we are aware of by the error curve. You can see that some biomarker may perform better in one data set but not the other. But in general, that our type biomarker achieve a robust and consistent better prediction power than all the other biomarkers. So we also look at the overall the predict power of our biomarker with the overall survival. You can see that like our type biomarker prediction, it also have a significant predict power on the overall survival for both anti-PD-1 study and anti-CTLA-4 study. So in summary, that in this study, we use a statistical approach to repurpose the previous published clinical data with no immunotherapy. However, after this repurpose, we can build a kind of reasonably robust biomarker to predict the immunotherapy response. Of course, ideally, we hope we could have some bigger cohort, but using the public data until now is the best we could do. And this is still ongoing work because like many kind of top score genes in our list are kind of very interesting. And my collaborators Shengqing Gu and Pan Dong from Pinifig lab is doing some downstream validation of some potential new regulators of immunotherapy resistance. So last of all, I would just thank all of these fantastic collaborators and PIs, like my mentor Shirley Liu and Gu Shengqing from our lab, and also Kai and Pan Dong, so for their like further experimental validation and very inspiring discussions. Thank you so much, everybody.
So how many genes used as a biomarker in your
whole genome? So it's a whole genome biomarker. So we do the whole genome correlation as a prediction value.
Quick comment and a quick question. So I think there are more data available. For example, Andy Kutriel published a relatively large study on anti-CTLA-4, anti-PD-1 melanoma, where RNA-seq data is available.
Really?
Yeah, it's about 6 months ago.
6 months.
And actually, they don't see any correlation between mutation and low-end response, but that's a
You mean like so you can see the name again?
Andy Kutriel.
And you mean Jennifer Barlow from? I know.
I'm not sure I remember the first author name, but I can after talking.
Okay, yeah, maybe I'll follow up.
And there were. The other one is that the Heining lab, and Nikra Stiefel published a number of CRISPR series for genes that are modifying,
exactly.
checkpoint inhibitor therapy. So, do any of those genes come up in your gene list, especially the first one, not the second one? I would assume.
Yeah. So like for Nick Heining, their top genes are PDPN2 and HLA-E. Like I'm just talking about their human gene name. Both of them are highly scored by our interaction TD dysfunction score. So it's very consistent.
And the strange Restifo genes?
Yeah. So for the Restifo genes, like SOX10 and Melena are all the genes from their screen. Like you can see, like Melena is one of the top screening hit, and also like the SOX10 here is also one of the top. Yeah. So we also check that screen only tell you the positive selected genes because their killing efficiency is too high. But for their top 3 genes, it's very consistent with our scoring model.
Have you looked at any dendritic submarkers or any of the transcription factors that make good dendritic cells?
Exactly, we look at that. There are some studies of functional dendritic cells and non-functional dendritic cells. And these biomarkers are very predictive in melanoma. But in some other cancer types, their prediction power is not that robust. This is why we haven't included that. But maybe as you mentioned, that even though they perform well in one cancer type, maybe that's enough. Like, do you have any good suggestions of some dendritic literature I should look at?
There's a transcription factor that Gajewski focused in on. Is it BAT, B-A-T?
BATF?
I believe so.
Yeah.
It's that one. The other is there any effort to subgroup tumors into common responsiveness types?
Common responsiveness?
As you said, it predicted well in melanoma, but not others. Is there any way to divide into tumor groups which have similar responses?
Similar responses across different cancer types.
Yeah, could you put together, for instance, melanoma, colorectal, and breast in a group that would have a higher correlation? So
I see, yeah.
if you take your tide value
Yeah.
and take out one tumor type,
Yeah.
does it improve or decrease the score?
Really great question. We actually have lots of backup slides here. I guess we somehow address the question. So forgot to increase the slides. So the short answer is like the most reliable score we observed is a mixture of all of the top cancer types. Like we do observe our type score are more similar between certain kind of cancer types. So for example, like AML is pretty different from melanoma and triple negative breast cancers. Like we do observe this kind of similarity, but we haven't pursued that deeper, but maybe we should, as you suggested.
If you did a graph of correlation and the 20 tumor types,
Yeah.
you know, which would be high and which would be low?
So like for the top 5 tumor types that our method could have the best signal to noise ratio, they are actually all pretty similar. And this one is a little bit outlier to the other 4, but their overall Pearson correlation are all positively correlated with each other. Maybe the melanoma and the triple negative breast cancer in terms of our dysfunction score are more similar to each other.
But you had like 20 tumor types in the analysis.
Yeah.
Or,
But-
yeah, I'd be curious to see a graph of the all 20.
So I would say that we do start with lots of tumor types. We don't have that here, but a limitation of our approach is actually here. So for some tumor types, our method may not really work because for computing, the overall survival is our endpoint we are looking at. But overall survival are very noisy. The patient may have overall survival simply by the difference of treatment afterward. So we look at whether our statistical test could have a really strong signal, meaning a very significant p-value on a portion of genes, but not significant p-value on most of the genes. For lots of the data sets that we collected, we don't see such a strong signal to noise ratio that our computation people use a lot. So this is why we can only get reliable results on 5 cancer types. And for most of cancer types, such as lung cancer, which is very important, our methods are limited in terms of the signal to noise ratio issues. So ideally, we hope we could do that, but by the data noise, sometimes we still don't have power to get the inter-tumor response subgroup as you suggested. Shocking.
So your scores, test score, actually usually just based on the expression.
Yeah, only expression.
So what about if you combine with those mutations or
Yeah.
topic numbers, you can also do
So
better.
combined with mutation, that definitely get better. Yeah. So we haven't we actually tried that, but we just don't show the data here because our ideal goal is to make something similar to the MAMA group. It's just a qPCR test. We don't need anything else to get the prediction point. And yeah, but if we have a mutation about merging them together, definitely will improve the prediction accuracy.
Okay, nice talk. If I understand correctly, you developed the tool titer, and you use that tool. Then you use, for instance, the patient, I got the tumor, I just do PCR like that, and then use your titer to test the correlation with this mutation or with this.
With the survival, with the responder status.
For the case, you titer should depend on the current publications.
Yeah.
This how can you convince that? How can you convince that?
So
The
first
real disease or cancer.
so do you mean like so for the evaluation?
Because if you go to your slide,
Wait.
this slide, this one.
Yeah.
So this number is the publications.
Oh.
What does it mean?
So
No,
even for
no, yeah. So, no.
this one?
Yeah, 22937.
Oh, I see. So this
So
is.
how can you, this was this mean? This is a publication. Some publication, you know, it's not make any sense. I mean, I don't, I try to understand what you
Oh yeah. So maybe I need to explain this better. So we build up a biomarker, and then we want to see whether our biomarker can predict the checkpoint blockade response, right? So then we use this kind of public data where they have both an RNA-seq and a responder status, and we use this data set to try whether we can, like if we assume we don't know the responder status, we can predict that. So these two data sets are our validation data set for our type biomarkers. Yeah. So, but for training of type, we don't really need the responder status from any immunotherapy. You can just use the historical large amount of clinical data. Yeah, so just in short, these two papers are just the evaluation data.